updated while I am using the function itself by using in place is equal to true. And after dropping all the missing values, if you look at the size of the data frame, it is turned out to be 1096 observations with 10 columns. On the whole, we have removed around 340 observations from the data frame, and we are going to proceed with the analysis only with the 1096 observations with 10 columns. So now let us see how to create the scatter plot. So here we are going to create a scatter plot of price as age, and that will be built using the default arguments. So if you see the first line, I have given as SNS.set. That means that we are giving a theme to the background of the plot. The theme is being dark grid. That means that you will have a dark shade as a background of your plot, and you will as well have a grid. So you can basically set themes to your background, and dark grid is a preset Seaborn theme. You can as well set themes that are available from the Seaborn package, and you can set that under the style argument. And even by default, if you use SNS.set, it will give you a dark grid theme. So in order to do a scatter plot, the function to be used from the Seaborn library is regplot. Regplot stands for regression plot, and inside the function you have to specify the variables for x axis and the y axis. Since it is going to be the scatter plot of price versus age, we need to give age under the x axis and price under the y axis. We are going to check how price varies with respect to the age of the cars. So here if you see, I have accessed the age variable from the data frame cars underscore data. Similarly, I have accessed the price variable from the cars underscore data. So this would be the output that you will be getting by setting the style as dark grid and by giving x as age and y as price. And if you see here, as the age increases, the price decreases, and the age that we see here is not in terms of years, but it is in terms of months. So 70 represents the car's age is around 5.8 years, and 80 represents the car's age is around 6.6 years. So in that case, most of the cars or the price is really low whenever the car's age is beyond 5 years, and the price is really high for the new aged car, because the car has traveled a lot, there could be more damage to it, and since it is not new, the price is also coming down. So it is very obvious from the logic perspective as well as from the data perspective, as age increases, the price automatically decreases. And if you also see, there is a regression line which is plotted over the scatter points. That is because by default fit underscore regression is equal to true in regplot function. What it does mean, it basically estimates the coefficient of x and then plots a regression line over the points. That is why the function is named as regression plot. And if you don't want to consider this regression fit line into your scatter plot, if you just want the scatter plot of any two variables, you can also do that. Like here we are going to do a scatter plot of prices age without the regression fit line. That is very easy. You can retain the same command as the previous slide, but you just need to add another parameter called fit underscore regression, and you can just set them to false, because as I mentioned earlier, by default it is true. That is why you got a regression line over those scatter points. But if you set it as false, you won't be getting the regression line, rather you will just get the scatter plot of price versus age. So and here if you see the plot, age is called as the label to the x axis and price is called as the label to the y axis. Here we have not specified any labels to x and y axis. It is already being shown here. That is how, because it takes the labels from the variable name that we have already given here. And the values 0, 10, 20, 30 are the values from the variable age, and from the plotting context these are called x tick labels, and 5000, 10,000 and so on are called as y tick labels, since that is on the y axis. The boxes are called as grids, and the points, the scatter points are called as markers. Here we have a solid round points. So now we are going to see how to create a scatter plot of price versus age by customizing the appearance of the markers. Appearance of the markers in the sense you can change the shape of your markers to differentiate between the categories. But here I have just taken only the scatter plot of price versus age. So, I am going to change all the markers into a different shape. So, in that case I can do that using the argument called marker, and inside the marker argument you can specify the type of marker you wanted to have it in your scatter plot. Here since I have given the asterisks, all the scatter points will be marked as stars. This will be very useful whenever you want to differentiate the points with respect to different categories that are available under a variable. Other than that, all the codes remains the same. I have just added marker is equal to star, that should be given under the single or double quote. So, in this example we are going to create a scatter plot of price versus age by fuel type. By fuel type in the sense we are going to add one more variable into the scatter plot, that is the variable fuel type. Why are we going to add that? Because it is of interest to check the relationship between price with age by adding another variable fuel type, like how price varies when the age increases with respect to different fuel types of the car. So, that can be added by using the parameter called hue and including the another variable to show the fuel type categories with different colors. Here we are going to add fuel type under the argument or parameter called hue, and we are going to represent the fuel type with respect to different colors. So, here we are going to do that by using the command called lmplot, that is from the Seaborn library. Lmplot is a function which combines regression plot and phased grid. It is very useful whenever you want to plot a scatter plot by doing conditional subsets of data or by including another variable into the picture. In that case lmplot will be very useful, and here the x axis is age variable and the y axis is the price variable, and the data from which we are going to access is the cars underscore data, and I have also set false to fit underscore reg, so that we do not get a regression fit over the scatter points. And here I am adding one more variable into the scatter plot using the hue parameter, and since we are going to add one more variable, points are going to be differentiated using colors based on the fuel type of the car. In that case we need to know which color represents what category. In that case I need to have legends as well. So, I have set legends as true, and you can also set color palettes using the different color palettes that are available in the Seaborn library. One of it is called set1. So, I have just used set1 as the color palette to color the data points based on the fuel type. So, this is what the input is about. Let us see what is the output that we are getting. So, this is a scatter plot of price versus age by fuel type. It is the same scatter plot, but here we have just differentiated the data points using the categories that are available under the fuel type, but we have just differentiated the data points based on the fuel type categories. So, the red represents diesel and the blue represents petrol and the greens are CNG. So, if you see here there are more data points or there are more cars that are of petrol fuel type, and the price is really higher for the cars which has diesel fuel type, and the price is comparatively lower for the cars which have CNG fuel type. And you can also check the relationship between price and age, as we know that whenever the car's age is high the price is very low, whenever the car's age is low the price will be high. Similarly, you can also custom the appearance of the markers using transparency, shape and size, like how we differentiated the points using colors here, different levels of transparency to the points to represent the categories. You can also do the same thing by giving different shapes and by giving different sizes for data points. So, this will help you include more variables into a single plot, or you will be able to understand the data quickly rather by looking at the numbers. So, next we are going to look at a plot called histogram. So, we are going to plot a histogram with default kernel density estimate, because using the Seaborn library by default it gives you a histogram with the kernel density estimate. So, the command that needs to be used is distplot, that is the representative of distribution plot. Since that is from the Seaborn library, I have used sns.distplot, and the input should be any numerical variable or any continuous variable, because histogram can be plotted to check the frequency distribution of any continuous variable. In that case, age is one of the continuous variables from the data frame. Here we are interested in looking at the frequency distribution of age, how the values are distributed under the age variable. In that case, you can use or you can access the age variable from the data frame cars_data. So, this is being the representative of the x axis. And as you know, by default it gives you the kernel density estimate, it gives you a curve over the bars, which is the representation of the distribution of the variable age. And on the y axis you have the kernel density estimate, but if your interest is to get the frequency distribution in terms of counts or numbers, then you can also get rid of the kernel density estimate and then have the counts on your y axis. Let us see how to get that. So, here we are going to plot histogram without the kernel density estimate. You can do that by setting KDE is equal to false. So, if you give that, the output would be similar to this. On the y axis it is just the representation of frequencies or the counts. On the x axis you have the range of values from the age variable, and you have too many intervals here. It is very difficult to interpret from this plot. The range is about 75 to 80, where the car's age is more than 6 years. The count is really high, and there are very few cars which are new. That is what we can interpret, because there are two extremes here, one is really high and one is really low. So, in that case you can also have a control on how many number of bins you want to have on the plot. So, that by having the control on the bins you will be able to quickly interpret from the distribution of your age variable. Let us see how to fix the number of bins. So, here we are going to plot the histogram with fixed number of bins. So, retain the same codes as in the previous slide. You can just add bins is equal to 5, so that you will have only 5 bins in your histogram. Bins are nothing but the range or the intervals. So, from this plot, by having the number of bins as 5, it is very clear that the frequency is really high for the bin value 70 to 80. That means that wherever the car's age is above 5 years, the frequency is high, because most of the car's detail is about the cars whose age is about 70 to 80 months, but you have only very few cars which are very new in our data frame. That is why the frequency is very low in the range between 0 to 50 months. So, next we are going to look at the bar plot. So, bar plot is basically to check the frequency distribution of any categorical variable. Here fuel type is one of the categorical variable in our data frame. So, let us look at the frequency distribution of the fuel type of the cars. So, to create a bar plot, count plot is the function that needs to be used. Under the function you just need to give the variable of interest, that is fuel type, and you can also specify from which data frame that you are accessing it from. It is cars_data. So, it is straightforward. You will get the output. You are getting the fuel type on your x axis and the count on your y axis, and the bars are the representative for the counts with respect to each fuel type. So, it is very evident from the plot that most of the cars have the fuel type as petrol, and there are very few cars whose fuel type are diesel or CNG. So, now we have seen how to create the bar plot. So, here we are going to see how to create group bar plot. We are going to create the group bar plot of fuel type and automatic. We mean by group bar plot. So, here we are going to have the bar plot of fuel type by adding another variable as automatic. So, we are going to look at the frequency distribution of the fuel type of the car along with the interpretation whether the car's gearbox is of automatic or manual. So, let us see how to do that. We can use the same function as bar plot, that is count plot, and you can specify the fuel type under the argument x, and you can also specify the data frame so that it knows from which it should access the fuel type from. And by adding hue is equal to automatic, we are including one more variable into the bar plot, so that we are checking the relationship between fuel type and automatic. So, let us see what would be the output. So, here is the output. On the x axis you have the fuel type. You have different fuel types like diesel, petrol and CNG, and on the y axis you have the count. If you see the legend here, it has two values, zeros and ones, and the zeros are the representative of manual gearbox and the ones are the representative of automatic gearbox. So, if you see here, there are only automatic gearbox types whose fuel type is of petrol, and there are no cars available with automatic gearbox when the fuel types are diesel or CNG. If you recall, this is just the visual representation of the crosstab output that we have seen earlier in the lectures. So, we have used the crosstab function to arrive at the relationship between the automatic and the fuel type, where we have seen that in terms of numbers and we have tried to interpret that, but here using visualization we are going to interpret the same thing but visually. So, next we are going to look at box and whiskers plot. We are going to look at this box and whiskers plot for numerical variable. For if you have a numerical variable in your data frame and if you want to interpret more from the variable, then you can go for box plot, because the box plot will give you the visual representation of the 5 number summary includes mean, median, the 5 number summary includes minimum, maximum and the 3 quantiles. Those are first quantile, second quantile and third quantile. So, let us see what the quantiles are and what the minimum and maximum values are. So, how do we do that? We can create a box plot using the command box plot, that is from the Seaborn library, and since we are interested in getting 5 number summary of the price variable, I have accessed the price variable from cars underscore data and I have given that under the argument called y. So, that the y will be the representation of price, but if you give it under x, the x will be the representation of price. So, now let us see how the output will look like. So, as I have mentioned, since we have given price under the argument y, we are getting the price value on the x axis. So, now let us try to interpret the box plot. It is called as box and whiskers plot because it has box as well as the whiskers to it. The horizontal lines are called as the whiskers. Now, let us try to interpret this. This horizontal line is called as the lower whisker, or also the representation of the minimum value, which is excluding the outliers. If you have outliers in your data which are nothing but the extreme values, then it excludes that values and then gives you the picture of what is the minimum value of the price. The minimum value of the price of the car is about 5,000 euros, and the upper whiskers, which represents the maximum value, that is excluding the outliers. So, the maximum value of the cars is around 16 to 17,000 by excluding the outlier or the extreme values, and these are called lower whisker and the upper whisker. The lowest horizontal line of the box represents the first quantile, that is 25% of the car's price is less than 8,000, and the middle line represents the second quantile, which is nothing but the median. That means that 50% of the data is less than 10,000 euros. And the upper horizontal line is nothing but third quantile, that is Q3, which represents that 75% of the price of the car is less than around 12,000 euros. This is called Q1, Q2 and Q3. And whatever the points that are lying above the whiskers are called as outliers, and you can also have the values below the whiskers as well. If you have points above the upper whisker, then you can say that these are outliers or the extreme values, where the values are really more than the 1.5 times of your Q3. This is what the Q3 value is about. The Q3 is around 12,000. So, these values are 1.5 times of Q3, that is why it is called as extreme values. It is not in between the range of the price, that is why it is called as the extreme values. Similarly, you can ask what happens when you have some values above the lower whiskers. In that case, those are also called as outliers or extreme values, because those values will be less than the 1.5 times of Q1. So, using box plot, you will be able to visually look at the distribution of the price variable and what would be the median value and what are the quantile values of the price. And using the box plot, the main key point to the box plot is you will be easily able to identify the outliers of any numerical variable. So, this is how we create a box plot, and this is how we interpret the box plot as well. So, now we are going to look at the box and whiskers plot for numerical versus categorical variable, because box and whiskers plot is very useful when you want to check the relationship between one numerical and one categorical variable, like how the price varies with respect to the another variable. Because in the previous example we have just looked at the distribution and how do we detect the outliers using the box plot. Here we are going to check the relationship between two variables. In that case, you can use box plot. You can use box plot when you have one numerical and one categorical variable. Here we are going to look at the price of the cars for various fuel types of the cars. So you can use the same command as in the previous slide, that is box plot, and under the x argument I have given fuel type, and under the y argument I have given the variable as price. So you have fuel type on your x axis and you have price on your y axis. And by looking at the plot, it is very evident that the price varies with respect to different fuel types of the cars. And as we know that the middle line is the representation of the median, if you look at the middle lines of the different fuel types of the cars, the median price of the car is really high when the fuel type of the car is petrol, and the median value is really low when the fuel type is of either diesel or CNG. It is very evident that on an average the petrol fuel type has the highest price among the cars from the data set that we have. And you can also see the maximum value of the maximum price of the car is for the diesel fuel type, and the minimum value of the car is also for the diesel fuel type. So these are the interpretation that you can make here, and you can see there are some extreme values that are above the upper whiskers of the diesel and petrol fuel type, and those are called as the extreme values because very few observations are there, and those are above the 1.5 times of your third quantile, that is 12,500 euros. So now we have checked the relationship between fuel type and the price. So now we are going to look at the grouped box and whiskers plot. Here we are going to look at the group box and whiskers plot of price as fuel type by including one more variable called automatic. So let us see how to do that. The codes remains the same. Whenever you want to have a grouped box plot, you just need to add that variable including the argument called hue, and I have added automatic under hue. So we will have a group box and whiskers plot. Let us see what the output is about. So here you have the same box plot as the previous slide, but you have another boxes which is corresponding to the different fuel types, and you have another boxes which are the representation of the automatic variable. Here if you see, the automatic variable is being included here, and the zeros are the representative of manual gearbox and the ones are the representative of automatic gearbox, and those are represented by blue and green in color respectively. So here whenever the car's fuel type is petrol and the gearbox type is also automatic, there are no cars that are available for the automatic gearbox when the fuel type is of either diesel or CNG. That is very evident from any of the plots that we have seen in the previous slides as well. Till now we have been looking at having only one plot in a window. We can also have multiple plots in a window. Here we are going to look at the box and whiskers plot and the histogram on the single window. So let us plot box, whiskers plot and histogram on the same window. So in order to do that, we have to first split the windows into two parts. What do we mean by splitting the windows into two parts? This is what we mean. So this is a single window. I have just splitted the window into two so that I can plot two plots in the same window, and it will be easier for me to interpret from the two plots instead of creating different plots for the same variable. I can as well do that in the same window itself. So here if you see, there is only small space for the upper part and there is a large space for the lower part. That is how, because I have set the aspect ratio with just because I have set the aspect ratio accordingly. Let us see how to split the window with giving let us see how to split the window, plotting window, and we will also see how to customize the aspect ratio. So subplots is the function that is used to create the subplots, and by giving 2 you mean that you need to have 2 rows. So you want to split your window into 2 parts in row wise, and by giving specification of grids using grid spec underscore kw, you can set the ratios of your height. I have given 0.15 and 0.85 so that there is a larger space for the second window and there is a less space for the first window. I have just splitted my window into 2 and given the aspect ratio, and I have saved that output to two variables called f and axis box plot and axis for histogram, because these are going to be same for both the box plot and the histogram. Combinedly I have saved it to 2 objects, and I have also saved it to a figure. So, AX underscore box represents the axis for box plot and AX underscore hist represents the axis for the histogram. So, let us now we can add or create two plots. So, the codes remains the same, because for creating the box plot you have to use the box plot and the variable of interest is price, and using the axis AX underscore box. And we have also created the histogram using the dist plot function, where we have specified the variable as price and where we have also specified what is the axis for that, that is using the same axis, that is AX underscore hist, and we wanted just the histogram with not the kernel density estimate. So, that is why we have set KD is equal to false. So, let us see how the output will look like. So, this is the output for the first command using the box plot. You are getting the box plot for the variable price as well as you are getting the histogram for the variable price. So, here this is a histogram of price as well as the box plot. So, you will be able to look at the frequency distribution of any continuous variable as well as the file number, as well as you will be able to look at the visual representation of file number summary of it. If you want to look how the outliers are present in a variable and what is the minimum and maximum value of a variable. So, all these information can be get using a single plot when you create plots using subplots. So, now we will see how to create pairwise plots. Pairwise plots are used to plot pairwise relationships in the data, and basically it creates the scatter plots for joint relationships and histograms for univariate relationships. We will understand what do we mean by joint relationships and univariate relationship when we look at the output of it. So, to create the pairwise plot, the command that is used is pair plot, that is also from the Seaborn library, and you can also specify the data frame, because on the whole we are going to look at the relationship between all the variables, considering all the variables, and the kind of plot that we are going to plot for any numerical variable is scatter, and we are going to color the data points using another variable called fuel type. So, now let us look at the output of the plot. So, this would be the output of your pairwise plot. You basically have the all possible relationship using all the variables. So, the first plot is like the distribution of the price, because on the x axis you have price and on the y axis also you have the price variable. So, this is called as joint relationship. Whenever you have same variable on both x and y axis, then you call it as joint relationship. In that case you will just have the histogram of it, like to indicate the frequency distribution of the variable price. But here the next plot, if you see, the y axis is price and if you look at the x axis it is age. So, this is actually, so when you move from left to right, whatever you have in your x axis is the representative of the x axis, and whatever you have it in your y axis is the y axis variable. So, this is the scatter plot of prices as age. It is very evident that as the age increases, the price decreases, and all the colors are the representative of various fuel types of the cars. So, similarly you will be able to interpret it for the other variables relationship, and if you see, all the diagonal boxes are histograms, because all the diagonal values represents, all the diagonal boxes represent the univariate distribution, because this is just the distribution of the variable age and this is just the distribution of the variable kilometer, and the distribution of the variable is HP is being represented here. So, the pairwise plot is used to get the plots for all possible combination of variables, and you will be able to look at in terms of scatter plot and histogram. This would give you an easier way to understand the relationship that exists between different pairs of variables. You can also see there is a legend which is shown here for the fuel type, like how the markers have been colored. So, now we have come to the end of the session. Let us summarize whatever we have learned till here. So, we have learned how to create the basic plots using the Seaborn library. The first thing that we have seen is how to create scatter plot, and then we have seen how to create histogram using the Seaborn library, and we have also looked at how to create simple bar plot, and then we have seen how to create grouped bar plot. Followed by that, we have seen how to create box and whiskers plot, and also we have seen how to create group box and whiskers plot. At last, we have seen how to create the pairwise plot from the Seaborn library, which was very useful to look at the relationship of all the variables in a single window. So, thank you.
समाज द्वारा दी हुई घर परिवार की जिम्मेदारी औरत अब तक बखूबी निभाती रही है। अब सवाल ये है कि क्या समाज उसको अपने पंख फैलाकर एक नई उड़ान भरने की इजाज़त देगा, जिसका पहला कदम ही शिक्षा है। आइए मिलते हैं एक गांव और उसकी बदलती हुई सोच से।
पहले कौन पढ़ाओ लिखाओ था, खेती क्यारी काम में डांग ढोर में ऐसे करें थे। पहले कौन गौर करे था लड़कियां पढ़ाने की, लड़कियां तो घर से बाहर भी निकाल देते थे हमारे जमाने में।
कितनी साल की उम्र में आपकी शादी हो गई?
मेरी जब तक शादी थोड़ी उम्र में कर दें, 16 साल की थी शादी करी।
तो लड़कियों को पढ़ाओगे अब आप आगे?
ये आजकल के बच्चे तो सब पढ़ाओ हैं। वे हमारे जमाने थे इसे जो खेती करें थे, भैंस रखें थे, ये तो कोई रखता है नहीं, बच्चे उनके माँ बाप वो ना रखें गाय भैंस।
मेरे 4 लड़की है, 2 लड़की की तो शादी कर दी, 2 लड़की के पढ़ाती हूँ। मेरी मन है जो हमारी लड़की जितना पढ़े उतना पढ़ाऊँ, आगे पढ़ाऊँ, आगे बढ़ाऊँ। हमारी लड़की पढ़ने चाहती है, पढ़ने में भी सही है। घर में इतना भी काम न देती हूँ, मैं पढ़ने के टाइम ज़्यादा देती हूँ, जो पढ़े हमारे बच्चे पढ़ के आगे बढ़े। और बच्चे तो आगे उनका भविष्य में तो खूब पढ़ाने चाहती हूँ। वो लड़की कहती है मैं डॉक्टर बनूंगी। बच्चे के ड्रेस मिलते हैं, पैसे भी मिलते हैं। बच्चों के पापा कहते हैं जब पढ़ो बेटा खूब, जितना पढ़ो मैं पढ़ाऊँ। पापा तो इनका मेहनत करते हैं बच्चे पढ़ाने के लिए।
आपका नाम क्या है?
सोनी।
कितने बच्चे हैं आपके?
3।
कौन, लड़कियां लड़के?
नहीं, 2 लड़की 1 लड़के।
आप पढ़े लिखे हो?
नहीं।
और आपके हस्बैंड?
नहीं, वो तो है 4-5 क्लास पर है।
तो आप बच्चों को पढ़ाना चाहते हो? तो अपनी बेटी बच्चों से मिलाओ हमें जरा।
हाँ, ये लड़की मेरी बड़ी वाली पूजा।
कौन सी कक्षा में पढ़ती है?
12th।
ये दूसरा दीपक, ये आरती है।
कौन सी कक्षा में पढ़ती हो?
9th क्लास।
9th क्लास में पढ़ती हो। तो आपको पढ़ाई में कौन हेल्प करता है? मम्मी पापा तो आपके इतने पढ़े लिखे नहीं हैं, तो आप मुझे ये बताओ कि आपको कैसे मदद मिलती है पढ़ाई लिखाई करने में? आपको दिक्कत आती है?
नहीं, स्कूल में टीचर्स पढ़ाती हैं, वो ट्यूशन्स लेती हूँ तो उससे करते हैं।
उससे आप पढ़ाई करती हैं? अच्छा, क्या बनना चाहते हो?
न्यूज़ रिपोर्टर।
ऊंची आवाज में बोलो।
न्यूज़ रिपोर्टर।
न्यूज रिपोर्टर। कि आपको लगता है आपके बच्चे जो बनना चाहते हैं आप उनको उतना बढ़ने देंगी, पढ़ने देंगी?
हाँ, पढ़ने दूंगी।
और शादी वादी का तो नहीं है कुछ सीन अभी?
नहीं, अभी तो मैं सोचा ही नहीं शादी उदी के बारे में।
क्या लगता है कि लड़कियों की किस उम्र में शादी होनी चाहिए?
जब उम्र हो जब भी शादी करना चाहिए, उससे पहले तो पढ़ाई लिखाई जरूरी है।
अब आपको वो उसमें चेंज लग रहा है कि?
हाँ, मैं तो अपने आप में चेंज हूँ। मैं अपने बच्चे को समय पे ही शादी करूंगी। हाँ, जैसे पढ़ लिख के अच्छे बन जाए, कोई नौकरी कर ले, फिर अपने शादी कर लो। मैं यहाँ आई ना तो यहाँ पर देख देख के बदलाव आया से। हाँ, बच्चों को पढ़ाओ, बच्चों के अच्छे परिवर्तन लाओ। और
पहले पढ़ाई कम होती थी, लड़कियों को कम पढ़ाते थे क्योंकि गांव में स्कूल भी कम होते थे, दूर दूर स्कूल होते थे, 8वीं से ज़्यादा स्कूल नहीं होता था, आने जाने के साधन कम थे, इसी कारण लड़कियों को पहले कम पढ़ाते थे और अब आजकल आने जाने के साधन ज़्यादा हो गए हैं और स्कूल वगैरह गांव-गांव में हो गए हैं। अब गांव में स्कूलों में से जो लड़के छोटी क्लास में पढ़ते हैं उनको किताब कापियाँ मिडिल तक मिलती हैं और वजीफ़ा भी मिलता है। और आजकल बच्चों को पढ़ाने में लड़कियों को तो ज़्यादा ही पढ़ाना चाहिए, क्योंकि लड़की पढ़ाने से घर में लड़की रहती हैं या बहू रहती हैं, वे लड़कियां अपना जो बाहर से कोई चिट्ठी पत्री कोई कागज़ आता है तो उसको पढ़ कर के भी बता सकती हैं। जैसे मेरी पोती है, वो छोटी वाली तो यही कहती है हर बार मम्मी पापा मैं तो डॉक्टर बनूंगी।
मेरा नाम आबद हेमीवाल है और मैं फार्मेसी परस्यू कर रही हूँ एंड साथ में मैं MBA एंट्रेंसेस के लिए प्रिपेयर कर रही हूँ।
तो आपको अपने घर से पढ़ाई करने में पूरी सपोर्ट है?
यस
पूरा सपोर्ट मिलता है?
पूरा सपोर्ट मिलता है मुझे घर
किस
वालों
तरह से, थोड़ा सा बताएं इसको।
आई मीन फाइनेंशियली, मॉरली, हर तरीके से मुझे सपोर्ट करते हैं और जो भी मैं आगे करना चाहती हूँ उसमें हमेशा सपोर्ट करते हैं।
आपको लगता है कि आप आगे जाके कुछ जॉब करेंगे?
हाँ
कुछ बनना चाहते हैं?
हाँ जी, आई वॉन्ट टू बी अ मैनेजर ऑफ अ गुड फार्मास्यूटिकल कंपनी।
आज देखती हूँ तो मेरे को ऐसा लगता है कि मैंने उस टाइम पढ़ाई छोड़ के बहुत मतलब गलत किया। तो मेरे हस्बैंड भी बहुत हेल्प करते हैं, वो खुद ही चाहते हैं कि बच्चे मेरी बेटियाँ मतलब अच्छा पढ़ लिख के अपने पैरों पे खड़ी हो, किसी के मतलब तरफ मतलब किसी के ऊपर डिपेंड नहीं रहे। अब तो क्या जागरूकता बहुत हो चुकी है, तो अब तो बड़े बुजुर्ग भी चाहते हैं कि बच्चे पढ़े, क्योंकि आजकल देखते ना लड़कियों के साथ क्या हो रहा है कि हमारे रिश्तेदार में भी ऐसा किया, लड़कियां मतलब शादी कर देते हैं, लड़के वाले परेशान करते हैं, उनको मारपीट करते हैं। तो इनके पापा तो कहते हैं अगर ऐसा तुम्हारे साथ ना हो इसलिए तुम पढ़ो, अपने इंडिपेंडेंट रहो, अपने पैरों पे खड़े रहो, किसी के मतलब ऊपर डिपेंड मत रहो।
चेंजेस तो आए, मतलब पिछली जनरेशन से अब देखे तो बहुत चेंजेस है और चेंज होगा ही, चेंज होना ही पड़ेगा।
इस गांव में मजदूर से लेकर किसान तक और दफ्तर जाने वालों से लेकर व्यापारी वर्ग तक हर किसी की सोच में कुछ तो बदल रहा है। शायद इस बदलाव की सबसे बड़ी वजह यह भी है कि औरतें खुद अपनी तकदीर बदलने की ठान चुकी हैं। न जाने कैसा था इंकलाबे सहर का आलम, बदल रही थी नजर कि मंजर बदल रहा था। आओ एक बदलाव हम भी लाएं, बेटियों को प्यार और सम्मान दिलाएं।
Swayam Prabha, Digital India, Educated India.
Hi, welcome back to the lecture series on GPU architectures and programming. In the last lecture, we have covered how OpenCL kernels can be partitioned across multiple devices and executed in case, and when it is advantageous, and how that helps in terms of exploiting more concurrent execution. And we have also understood that this is a facility available with OpenCL because the OpenCL kernels are, in case the vendor provides an OpenCL implementation for any device, the same kernel code can be mapped to different possible devices, provided you have suitable OpenCL libraries in those devices. The next topic we like to touch in is how to use this concept in a general case where you have a application DAGs for directed acyclic graph, and you want to execute this kind of an application on a system architecture where you have multiple devices. So what we are assuming in this small example is, say this is a task graph. So you have 3 input buffers A, B and D. So you have two kernels who can execute initially in parallel. Let's say K1 and K2. K1, let us say, this is again an example, it performs matrix multiplication. K2 takes one input buffer, for all the elements it performs square computation for each of the elements, and they produce their outputs in buffer C and E, and these are basically buffers which are input buffers for the kernel K3, and this kernel will again perform a matrix vector multiplication. Let's say this is a workload for us, and we want to execute this workload on a system where you have a CPU and two GPU devices coming from the same vendor. So so we can set up a context with these multiple devices and set up OpenCL queues for each of these devices. So essentially we will have to write a host program which will create the context for the platform. It will create 3 OpenCL devices, each having their own command queues, and then you can enqueue the write, ND range and read operations for kernels K1 and K2 on 2 different devices that will run concurrently. Now you have to choose that suitably. Maybe you as a programmer understand that which kernel is more compute intensive, it has less divergence and all that, and accordingly you can make choices, right? So you can map this K1 and K2 to 2 of the devices, and you synchronize until both the kernels finish execution. So essentially you wait in the host code. Once both of the kernels finish execution, then you may want to, this is just an example mapping we are talking about, that you may want to map this data space, this input data space which is C and E, into 2 different GPU devices and launch 2 kernels K31 and K32 concurrently. So what we are suggesting is, so here you have the buffer C full of data produced by K1 and the buffer E produced by data produced by K2, right? So maybe we are again talking about a possible mapping. Let's say you have GPU device 1 and GPU device 2. You can copy a part of this here, right? A part of this here, a part of this here, a part of this here, and then you can launch a kernel K31 here, you can launch a kernel K32 here, produce 2 outputs, and then you copy it to the host side memory, right? Copy this to the host side memory to get the final output. You may want to do that because you have multiple such devices available, and in case this data transfer is not a big overhead with respect to the computational gain you make by execution in parallel. If that is so, then you will like to do this operation, right? So this is some possible mapping that you can make, and depending on the kernel's compute characteristics, it may have some advantage, right? So in general, we understand that DAC scheduling is a complex problem because you have a architecture with multiple kinds of devices. Each kernel may map in some specific way to some device, like kernel K1 may give some specific execution time in a CPU, it may give some different execution time on a GPU, right? So first, as a programmer, you need to identify what is a good device to do the mapping, and then you should like to set up the command queues and launch the kernels respecting the dependencies. For example, here as we discussed, K1 and K2 do not have any dependency, but the execution of K3 depends on K1 and K2, both of them producing their outputs. So I need to synchronize before executing K3, and then if required, if it's advantageous, then I may want to partition K3 and execute. So as we can see that there can be many possible options, like it may also make sense, let's say it all depends on the runtime scenario, that if K2 is producing something and K2 is mapped to a device, shall I map K3 to the same device? Well, when will I want to do that? So I will want to map K2 and K3 to the same device in a situation because then this data transfer overhead from K2 to K3 will not exist, right? So we have to figure out what is a good mapping. Well, I mean, in case K2 is idle, or then the device where K2 has been mapped is idle, then that also may make sense, right? So how to choose a mapping, what is the best mapping for a given application and an architecture is something that you have to fix. Here we are not discussing that problem, we are just trying to tell that, well, multiple mappings can be possible given an application and an architecture. As a programmer, you need to figure out what are the mapping characteristics, what is a benefit in which case, and accordingly decide. So we are just trying to motivate that if I map K2 and K3 together in a single device, it may be good because then I don't have this data transfer overhead. Or maybe when there is something else, maybe some other job is there for which I will like to use this device. So then I will actually like to use K3 to and map it to some other device, right? So it's all a situation which you have to fix based on the options and all that. So this was one example of DAG scheduling that we went through. Now, so overall, these are the factors that we like to consider, that what is the scheduling overhead, right? I mean, if we are scheduling multiple kernels in multiple devices, then we have to do some bookkeeping, like we have to wait on events, we have to perform data transfers. So these are the overheads which you have to take care of, and we have to say that, well, we will perform a scheduling decision only when the overheads actually, the benefits outweigh the overheads, right? So the other issue would also be that the granularity of workloads, that how much you will like to divide the problem. If you divide the problem into too many instances, then for each problem the number of threads become too thin to sustain any overhead that is associated with the kernel launch event. So this is also important, that whenever you are launching a kernel, that has some overhead with respect to the runtime. Whenever you are actually doing a notify callback, or you are executing a kernel based on the execution status of something else, that also has a context switch overhead. So all these switching overheads are there. So if you divide the problem into too many instances and try to solve it, then the overheads will creep in and far outweigh the advantage of parallelism that you may have, right? So these things one has to figure out. And also you have to take care of whether the execution, what is the execution performance of the different devices. So it's a heterogeneous compute platform. You may have multiple different GPUs. So a kernel executing in one GPU with a performance metric in a different GPU may have a different performance metric, right? So these are all factors that one has to figure out. The other topic we like to cover is device fission. It's like there are several CPU devices from different vendors which support this concept of dividing the device in the OpenCL runtime system into smaller sub-devices. For example, in general, if you have one CPU, OpenCL will identify it as a device, right? But an SIMD, a CPU, a modern CPU with multiple SIMD units can be logically partitioned to several sub-devices. In that case, OpenCL system can identify them as separate sub-devices and manage them separately, right? So till date, this idea of device fission is supported only on CPU-like devices, and it is possible to use device fission to build a portable and powerful threading application based on task parallelism. We will like to think that if there are such sub-devices, then they can actually perform, let's say, overlapped execution to provide a more to exploit task level parallelism and give us some optimized execution of a given SIMD kernel. So we will not go in great detail about executing a program in multiple sub-devices, but rather let's just discuss how to create such devices. So these are the options that are available till date in the OpenCL runtime system. You can use this API function CL create sub-devices, but how you want to create the device partition, there are several options. So you can create an array of sub-devices using this call. Each of the sub-device will refer a non-intersecting set of compute units. So suppose you have a set of compute units. In each sub-device you will have a set of compute units which will not belong to the set of compute units for some other device. And so this partitioning of device, the internal SIMD units of the CPU across subdevices has to be managed, and you can give as a programmer you can give different directives that how to manage them. So you can tell the runtime system that if you use this flag CL device partition equally, and then it will perform the allocation of compute units to subdevices following this flag. You can give it a by counts flag, and also there is this option of affinity domain, right? So there are different possibilities in which you can actually partition the subdevice space. Once the subdevices are created, they are very much like a normal OpenCL device. For them, you can create context, you can build programs, you can launch programs into command queues specified for such subdevices and all that, right? So these options you can just look into. We will just give a program example with one of the options, but of course these are quite intuitive. So and for a specific subdevice you can create a separate command queue, and if you launch a command, it will get launched not into the entire device but into that subdevice. So let's have a look into this simple program. So first thing, you have to set up a device property array, using which you are trying to specify how the subdevices are defined, right? So for this you have to define an array. Let's say we give it the name subdevice properties. Its type has to be CL device partition property, and you have to populate this array with the following elements. The first component has to be the primitive, like what is your choice of partitioning scheme. So let's say I choose CL device partition equally. You distribute the subdevices equally, and you have to specify what is the number of subdevices you want. So the first thing is CL device partition equally. So whatever is the number of units available, you are saying that, well, you divide them equally across the number of subdevices, and the number of subdevices you want is specified by this flag. Okay. So once this array is set up, you just make a call CL create subdevices. You give it the device ID and you pass your requirements to this array, and you give this thing, that is what is the total number of compute units you have, and divide it by the number of compute units you want per subdevice. And this call will actually provide back the handles to each of the subdevices inside this array subdevices. Okay. So once this is done, next let's look into how you can actually create queues and engage the different subdevices. So and also we like to say that here we are using the equally flag. Instead of that, I can actually give explicit counts, or I can specify an affinity domain, right? So coming back to the command queues, so this is the array in which I am trying to define command queues for each of the devices. So in the for loop, as you can see, we are firing this CL create command queue command, and the number of times this loop is going to rotate is exactly equal to the number of subdevices, which is the total number of compute units divided by number of compute units you want per subdevice. So that's the number of subdevices you have created, and for each of them you are creating a separate command queue, right? Now so that is how we actually create the set of subdevices, and you create separate command queues for each of the subdevices. Now what is the advantage of this, like we have been discussing? Well, now you can issue commands in parallel across the different command queues for the subdevices, and that will help you to achieve overlapped execution. In case you want one subdevice to do something, you want some other subdevice to do some other thing. Let's say you want subdevice 1 to do some data copy operation, while subdevice 2 is actually engaging to some executing some other kernel. So like once the subdevices are created, they are really going to act like normal full-fledged OpenCL devices to the programmer's point of view, right? So with this discussion about device fission and properties of subdevices, we'll like to end this lecture. Thank you.
Swayam Prabha. Digital India. Educated India.
Hi, welcome back to the lecture series on GPU architectures and programming. So, in the last lecture we have discussed how to create OpenCL sub-devices, how to perform DAC scheduling on architecture comprising multiple devices which support OpenCL and all that. Now, in this context, while we have been discussing how I can execute kernels in parallel, or how I can break down a kernel and partition it and launch into multiple devices, we will like to go back to our original choice of programming language, which was CUDA, and check whether in CUDA we have any support for such concurrent execution. If you remember, so by the way, this is the point where we can officially say that we are done with our discussions on OpenCL and heterogeneous computing using OpenCL. We are kind of going back to CUDA programming language and use usage for this purpose, and also in the future lectures we will be using CUDA for other purposes as have been provided in the indexes. So, the issue is, if you look at our earlier lectures on CUDA programs, CUDA runtime system and everything, our programming model has been you launch a host code, the host code executes sequentially, and it can launch a CUDA kernel, and then it will wait till the kernel returns, and then you can fire, and the host code can go beyond, and then it can launch another CUDA command, right. So, although the host code can launch the CUDA kernel and go beyond to the next command to be executed for the GPU, but the next command is going to will execute only when the kernel's execution is done, right. So, there is sequentiality in that way, but can I have CUDA applications sharing a GPU and working together? Because as we see, the issue is, if I look at a GPU, it is like an accelerator. It does not have any scheduling primitive from the software side, it is a hardware scheduler based device. So, you cannot launch, the way we have defined till now, we never had the facility that we will be launching multiple kernels together on a CPU, on a GPU device at the same time to execute in an interleaved way or something else. So, the issue is, can I have support for concurrent execution in CUDA? The answer is yes. In currently available CUDA runtime systems, you have such supports. So, and that is also desirable, because in then you can also extract the maximum parallelism that you have available in the underlying hardware. So, the way CUDA manages concurrency is by executing asynchronous commands in streams or CUDA streams, and each stream can execute a sequence of commands that have been dispatched to that stream in that order. So, in CUDA, the way we have been discussing till now, we have when we are talking about a CUDA program, there is something called a default CUDA stream. Okay, that's stream 0. In general, I can write a program which is engaging the CUDA the GPU by running multiple CUDA streams in parallel. So, the runtime system will use this abstraction of streams to execute CUDA commands in parallel, while each of the streams, while the host program will just issue commands asynchronously to each stream. So, we will see that why we call this asynchronous and all that. So, different streams, so the host program, as we are saying, instead of writing a normal CUDA program which is a single stream of execution, the host program can define multiple streams, and it can dispatch commands for the runtime system individually to each of the streams, and each of the streams will be executing those read, write or kernel commands in the order they have been dispatched, but in what order they do it among streams is completely defined by the runtime system. So, they will actually execute out of order with respect to each other, that is at the stream level. So, what is a CUDA stream? So, it refers to a sequence of asynchronous CUDA operations that execute in a device in the order issued by the host code. So suppose the host code is issuing a set of orders to CUDA stream 1, those will be executed by that stream in that order. The host code also issues some other commands to a separate stream. That stream will execute whatever commands has been issued to that stream in that order. But as I was saying, in what order these streams interleave is dependent on the runtime, and there is no finite control on that. So typically when I talk about CUDA commands, we are thinking of basic operations like host to device data transfer, host and device device to host data transfers, kernel launches, and synchronization commands that may be issued by the host, but they are handled by the device, those kind of commands, right? And the execution of operations inside a stream, that is asynchronous with respect to the host. Now this is the key point. So the host program just dispatches commands to different streams and moves forward, right? So these commands execute in a CUDA stream set up for the GPU device, completely independent of what the host is doing. The host has dispatched commands. It's very much like OpenCL command queue. You have the OpenCL host program moving forward, dispatching commands to command queues. You can have the CUDA host program moving forward and dispatching operations to the stream, right? So once they have been dispatched, the host program doesn't have a control. It's just moving forward asynchronously, right? So now it becomes the job of the programmers to actually use the CUDA APIs to ensure that these asynchronous operations can preserve dependencies. So here also, like OpenCL we have been discussing, here also we will see the role of events through which synchronization can be attained across streams and all that. So while speaking of CUDA streams, all CUDA operations, both kernels and data transfers, they either implicitly or explicitly run in a stream. So when we don't specify the stream, it's the default null stream, right? So these are the two different types of streams, the implicitly declared stream or the null stream, and the explicitly declared streams, which are the non-null streams. So by default everything is in stream 0, and otherwise if you want to create more streams for attaining concurrent execution, you have to define them explicitly. Okay, so the null stream is the default stream where kernels launch and data transfers are used. In case you do not specify it, and whatever, like we have been saying that whatever CUDA examples we specified earlier, they were all by default getting launched into this stream. So let's get our first test of this asynchronous API. So first we are just trying to give, we are just trying to give some basic examples of stream operations, like so the type is CUDA stream underscore t. So you can define a stream, you can declare a stream using this command, the first one, CUDA stream underscore t, then stream. So this is a stream that you have defined, and then after declaring it, you have to create the stream using a command like CUDA stream create. If you want to destroy an already created stream, you have to fire the command CUDA stream destroy. And if you want a stream to synchronize, and we will see that if it is required, you have to use the command CUDA stream synchronize. Now so when you want to synchronize, you actually block the host until all the streams has completed operations, right? So when we will see the different possible synchronizations. Maybe this is a good time to look at that, like just a minute. So these are the different ways you have synchronization on the stream. Right now we are just saying that let's say we just fire this command CUDA stream synchronize. Then you are asking that wait, if this is there in the host program, then the program will wait here until all the streams finish. If this is there in the host program, the first one is CUDA device synchronize. So if you are firing CUDA device synchronize in the host program, you want all the streams that are running in the CUDA device to finish, and then only the host program move beyond this point. If you want a specific stream to synchronize, then you just write CUDA stream synchronize with the stream name. That means the host program doesn't move forward until this specific stream will finish. The other ones we will see soon. So now let's go back to our example that we have started. So this is CUDA stream synchronize. So you have blocked the host program until and unless this stream finishes whatever operation it has been given. Here we have not given anything till now. So the other thing that you can do is you can query a stream right? I mean, this gives you an error status, or I mean some status which can say whether it's completed these executions, whether it's still in process and all that, right? So an important thing that we have to remember is when you want to perform data transfer to the CUDA streams, they have to be asynchronous. Why? Because unlike a normal CUDA program, if you are using CUDA streams, then your host program is moving forward just by dispatching commands, right? So for that, the memory copy operation should be done in such a way that it has to run in a separate thread with respect to asynchronously with respect to the real host program's thread of execution, right? So for that, unlike normal CUDA memcopy, you have to use this memcopy command, which is CUDA memcopy async, because now you really want asynchronous memory operation, that you don't wait at this point here until the memcopy is done. You just issue this command to a specific stream, let's say in this case is stream 0, and you just move forward, right? So this is the difference between a normal CUDA memcopy and CUDA memcopy async. This makes the transfer asynchronous so that the host program can move at its own speed, and this transfer can happen at own speed as is supported by the device, right? Now in this command, as you can see, well, you have a source, you have a destination, you specify in which stream to copy, and you give the size, and you also have a flag called CUDA memcopy kind, which is an enumerated type. It has the possible values, like we all know that earlier, I mean, these are also similar to the flags we have been using for CUDA memcopy, normal CUDA memcopy. So you can either do memcopy host to host, doesn't make sense maybe, and then you can do host to device, device to host, and if you want to do memcopy across multiple devices, then device to device, right? Now there is another important thing. When you are doing this work across streams, and then the requirement would be that you want whatever memory has been allocated on the host side to be pinned. So let's understand what we say here. Like, so let's say you have a host side memory and a buffer has been declared, and you want to copy it to a device side memory, right? So this is a host memory buffer, and you are copying it to a device. Earlier it used to be a single one-shot copy command, right? But now in the current form, since things are asynchronous, so the copy, you are actually leaving it to the copy engines on the device and the runtime system to manage asynchronously. So the copy now can happen as and when the runtime system wants to do it, while you are moving forward with the host program, and the copy operations are happening asynchronously, right? The point is they may not happen in one shot. It's not a blocking operation. So then, thinking from the operating system's point of view, it may happen that the copy operation started, some amount of data has been copied, and then when you want to restart, by that time the page in the host side OS memory where this buffer was sitting, it has been mapped out, right? So that will create unnecessary delay and it will be an issue. So what you want is, if you are allocating memory on the host side, this is the host side memory from which you are going to copy into asynchronous streams. You want this memory to be what we call as pinned. You want this memory to be pinned on the DRAM device, so that you are essentially asking the OS that, hey, you don't page it out, right? Because I am going to copy as and when I want in a lazy fashion, right? So for ensuring that the memory is pinned on the host side, unlike normal CUDA malloc, now you use the command CUDA malloc host. So these are the differences you can see: CUDA memcopy async, CUDA malloc host. So you use CUDA malloc host to have a pinned data buffer in the host side memory, and then you launch the kernel to a specific stream. So this is a new thing. Earlier you have been launching kernels, so you give a grid and block. Then as we can see, there can be a third parameter that, well, how much amount of shared memory in the GPU's SMs will be allocated for this specific kernel. That can also be specified by this shared memory size. Why? Well, you are having multiple streams, it is expected you can launch multiple kernels across streams. So you may want to specify well which stream working with which kernel should use how much amount of shared memory. Okay, so that's why you can specify the shared memory size reserved for this kernel and in which stream do you want the kernel to be launched. Well, so so this is how you can actually copy declare host side data data buffer, and then you can copy data. So this is not just I would like to remind you, this is not a sequence of program statements. We have just written these different directives to let you understand what are the different specific operations that the asynchronous API of CUDA is actually allowing you to do, right? So this is how you launch the kernel, this is how you malloc data to the host in a pinned fashion, this is how you perform asynchronous transfer, this is how you actually synchronize on a specific stream, and this is how you create or destroy the stream, and you can also query a stream status. Coming to basic CUDA stream program examples. So let's say you have a normal kernel. So all you are doing is you calculate the global thread ID and you just add that with a constant value, a simple kernel. So what we will do is we will also define a check function here, so that whatever function call we will make next in whatever programs we show you, the status that the function call returns can be is actually handled nicely through this check function. So we are actually doing this so that we can avoid writing all this handler code everywhere. So for every function call we can just give this call to check, so that whatever error type will be emitted, if in case it's not a success, it is gracefully handled with suitable file prints to the error standard error. So now let's look into the host program example for CUDA streams. So inside your main, you first declare these device properties, right? You have a variable for device properties, and you can check whether for this device properties for some specific CUDA device ID, what are the device properties, and then it will be able to say that well what is running in that in the CUDA device and all that. So if you look at an example of the prints we have here, so it's just going to say that well this is the program that you are running, and it's running in that this specific device with these capabilities and all that. So I believe earlier we have already talked about what are device properties, what are the different CUDA device properties and all that, essentially the information of the runtime system. So once I make this call using this, I can actually so through this call I am actually extracting from the runtime system all the device properties and storing them into this, right? And for some specific GPU device ID. In this case, we are just querying for the ID GPU device with ID 0. It can be whatever you want, right? So and then we have some standard prints just to tell what is the program name that is running, because it's again that is what should be the executable name in argv0 location. And you also print what is the name of the CUDA device, what is the GPU device on which you are running the program. So that would be in the device property structure itself, in the field device properties .name, right? So this is just normal bookkeeping code like we write. You have the device property structure, and you define a data type for that. You define a device property structure, and you extract the device properties for the target device. You print all those status flags, and then let's get into the normal action. So let's say you start with allocating host side memory using, as we have discussed, now we will be using CUDA malloc host command to get pinned memory, and then you can use normal CUDA malloc for the device side memory. Why use normal CUDA malloc? Well, then in the device side memory you don't have an issue with paging out of main memory and all that, right? So as you can see that we are making all those function calls under the guard of the check statement, so that any kind of error is gracefully handled, right. So once this is done, let's decide on some launch configuration of the kernel. So you define a block of size 512, you define a grid with this some specific number of blocks like this, like well so this is my definition of the grid, right. I mean, what is the number of blocks and all that. So once I have defined what is the total number of blocks that would be in the grid and what is the thread block size, then let's use the CUDA API event to perform some bookkeeping of the execution times. So I believe in our earlier lectures we have already discussed of the CUDA event API and how to use CUDA events to sample timings. So at this point you use this CUDA event create command to sample the current time in and store it in the event object called stop. And then let's say we get into the action with the different CUDA streams. So we'll just issue work asynchronously to the GPU, which is set to GPU stream 0. So what we are doing is we are just using the CUDA memcopy async commands to launch a copy operation from the host side array HA to the device side array using CUDA memcopy host to device directive, right. And as you can see that is an asynchronous copy, so we'll just immediately go forward to launching the kernel, and since no stream is explicitly specified, this all is happening in stream 0. And then once that is done, you expect the result to be in the in the device side memory. So you get back that data from the device side to the host side memory, and then you again you perform a CUDA event record again on the stop event, right. So so here you actually declare the CUDA event CUDA event object stop, and you actually created you use this API function CUDA event create, right, to define and then here you actually sample it, right. So from this point the event is ready and it has started sampling the timings, right, and you are actually measuring the time that has been sampled here in using this CUDA event record, right. Now after this you want the CPU to do some work while waiting for stage 1 to finish, that you are waiting for the stream to complete. So what you can do is you can keep on querying the stop, and whether it's at a state that is it's not ready, whether it's returning a not ready flag, and for the time being you are just making the CPU do some simple action like incrementing a variable, because as you can see that all the work of the memory copy is going on asynchronously to the GPU device and coming back. This is just there to keep the host side thread busy here, right. So once we know that well, from this event record we get to know that yes, things are done, you move forward. So from the on CUDA event query you get the stream status that yes, these commands have finished their execution. Then you actually print the CPU and GPU times. So you get out of this loop when you are actually querying this event, and you are getting that yes, the CUDA, I mean it's not really CUDA error not ready, this flag is no more true. Then you just print what is the execution time of the CPU, I mean what is the number of iterations that the CPU spent waiting for the GPU to finish, because that status will actually change when this all the commands that have been asynchronously issued to the GPU, they are all completed, right. So this is just telling you how many iterations of the loop happened for the time in which the GPU got the values, copied asynchronously, executed the kernel, and then copied things back, right, through the last mem copy from device to host side, right. So once everything is done, you just release the resources through a CUDA event destroy, because now this event tag is no more required. The CUDA event variable is no more required, and of course you can free the host side as well as the device side memory and perform a CUDA device reset. So this is just a basic example. All we are doing is we are doing the normal kernel operations, but just using asynchronous memory copy and asynchronous execution of the kernel. But yet we haven't really exploited the concurrency that is available on the GPU side device by using multiple streams. It was just about exploiting this notion of asynchronous dispatch. So now we will move forward with that and see how using multiple streams we can have overlapped computation of host and device, overlapped computation in the host, and also a data transfer happening between host and device. So these are the different possibilities, right, where I can have some action happening both in the host and the device, and in that way I have overlapped execution so that the total execution time reduces, right. So that's what we want to do. Now this is a listing like what are the things that are possible in parallel. Host is computing something and the device is also computing something. Host is computing something and you have some transfer of data from the host to device. You have similar transfers and also the device is computing something, or you have multiple streams that are executing in the device, right. So now these are the possibilities that you have. Now the typically common pattern that we have with respect to concurrent execution, the advantage of concurrent execution would be like this. For example, consider a normal execution of a GPU program or a CUDA kernel here. So you have a memory copy from host to device that will take some time. It's followed by the execution time of the kernel, and then you have time for memory copy from the device to the host side, right. Now suppose you break down these memory transfers to small chunks and you create different kernels for kernel versions, I would say, for operating on these chunks, right, and then you launch them in multiple streams. So as you can see that this is a pipelined execution. So now while kernel is executing for this first chunk of data that has been copied, in parallel you can actually have the GPU getting the data for the second instance of the data segment, right. So this small host to device computation is done, then the kernel is working on it in one stream, and in the other stream you can have the the second segment of data chunk coming in from the host side. Well, in hardware this should definitely be possible. So you need support, like in your GPU side you have a copy engine which is copying the data from the host, and you have execution units which are engaging the different threads and processing the data which have been already copied, right. So in terms of hardware this would be possible. That's why you can have this overlapped execution. Now since you have overlapped these executions of copy and computation, overall as you can see you have a performance improvement, and this is what we want to attain by launching things in parallel across streams. So in general, if we assume that we have a PCI Express bus through which data copy is happening, and of course we cannot support multiple copies in a PCI Express bus, then data transfers cannot execute concurrently, but although they are issued in separate streams, but the data transfer can overlap with execution of the kernel, as we can see in this example. However, there are devices with duplex PCI buses where I can have a support for two parallel data transfers, and in case they are in different streams and in different directions, they can happen in parallel. So let's say in stream 1 I have a H2D type copy, and in stream 2 I have a D2H type copy. That is considered absolutely fine. Okay, so with this now maybe we'll stop here, and we'll see some program examples like how these concurrent streams are useful in the next lecture. Thank you.
Swayam Prabha, Digital India, Educated India.
Hi, welcome back to the lecture series on GPU architectures and programming. So in the last lecture we have been discussing about CUDA streams and how overlapped execution can be performed across streams, and in that regard we have set up a nice example here of like how we can have overlapped execution in terms of it's better to say overlapping the execution and data transfer. And we also mentioned that in case we have a device where we have a support for duplex PCI bus, then I can overlap two data transfers happening in different devices and happening in different directions. So let's assume that we have a normal PCI Express bus, as is the case here. So we can overlap execution in the GPU device along with a one-sided data transfer. Now, if you are really engaging different streams to perform concurrent execution, you may also require sometimes to synchronize the executions, because in general streams are asynchronous. So for that, CUDA will provide you several synchronization primitives. In case you want the host program to wait till all the CUDA devices, all the streams executing on the CUDA device to finish, you can use the first option, CUDA device synchronize. If you want a single stream to if you want the host program to wait at a point where you want the single stream to synchronize, you execute CUDA stream synchronize with the option that you have to give the argument which specific stream you want to synchronize at that point. If you want to synchronize an event in a stream on a specific event in a stream, then you have to give this command CUDA stream wait event, right? So you are saying that, well, this stream should wait for this event to happen. So let us again enumerate the options. You want all the streams to synchronize at some point, so that's CUDA device synchronize at some point in the host program. If you want to synchronize a specific stream, you use CUDA stream synchronize. If you want CUDA stream wait event, you want that a stream will synchronize in a specific event to a specific event, then you use CUDA stream wait event. And if you want synchronizing across streams using an event, then of course you don't need to specify the stream, you just specify the event, and you have the command CUDA event synchronize just with the event argument. So you synchronize all the streams with this event. So now coming to our concurrency example, so we will try to see how overlapped execution can be attained. So let's say you have a main where this part of the code is again quite same. You get the device properties, you are saying that in which device what is executing and all that, and then you can perform, well, this is a piece of code that is necessary to figure out whether you have support for concurrent execution or not. So that's actually from the device property structure you can figure out the CUDA runtime system's major and minor number, and using these numbers you can figure out how much is the execution support. So in case the major is less than 3 and or the device major is equal to 3 and less than 5, well, in that case, in case it's less than 3, you don't have any support for concurrent execution, so CUDA kernels will be serialized. Now and also there is this issue with major and minor values. So based on this choice, what is the major and minor value of the CUDA runtime system, there would be your device property will contain whether the value 0 or 1 for the concurrent kernel's flag, and that would tell you whether there is support or not. And also there are two possible checks here. This is what I am trying to say, that you can have concurrent execution fully, or you can have limited concurrent execution. In the other case, which is this else, like you satisfy the major and minor requirements, like let's say you have major 3 and a minor less than 5, then in case your CUDA kernels is for those devices where the major version is earlier to 3 or it's equal to 3 but the minor number is earlier to 5, for those devices if you have CUDA kernels command set to 1, for the earlier devices the thing is you don't have a support for something called hyperq. So you will have concurrency support, but not fully. We will see what is that. And in case you are not getting inside this check, that means your CUDA runtime systems is saying that, well, for the GPU device you are talking about, the major number is greater than 3, or the major number is equal to 3 but the minor is greater than 5. For that you have compute capability and which is suitable for concurrent execution, right? So it will, your code here, the example we are talking about here, will just say that yes, you have concurrent execution capability, and it will also specify what exact is the major and minor value, and what is, so that would be a kind of indicator of what is the amount of compute capability supported, right? Now something you have interesting here, that what is this hyperq thing. So there are earlier GPU devices where you have support for concurrent execution, but that's limited. So let's try and understand what is this limitation. So consider this situation that, well, you have got streams and you have got multiple kernels which are executing on the streams. So you want to execute a task graph where you have the kernels A, B and C queued up, right? Let's call their instances the first, second and all the first instances of A, B and C. You want A to finish, then B to work and C want to work on the data that B produces, things like that. Maybe you have other instances of these kernels sequenced in some other stream, and you have the same kernel's third instances sequenced in some other stream. The issue is, in CUDA, older runtime systems, these streams will finally get into a job queue where things are pretty much serialized. So you may have, I am just drawing an option here, A1 followed by B1 followed by C1 followed by A2 followed by B2 followed by C2, so on and so forth. And then the system is trying to identify what is the parallelism available. It doesn't see any parallelism here because of these dependencies, doesn't see parallelism here because of the dependencies. It only figures that these are the two that can be really executed in parallel. Whereas we can see that, well, A1, A2, A3 can be executed in parallel, B1, B2, B3 can be executed in parallel, and C1, C2, C3 can be executed in parallel, right? So this issue with, the final hardware queue has been resolved with a architectural support of some structure called hyperq, through which it is actually able to see the dependency structure and see what is the full scope of concurrent execution that is possible across the different streams. So we are not going to more architectural details. You can read NVIDIA documents that are widely available. So for this example, let's first see that how things can be, how we can have overlapped execution. So what we'll first do is we'll figure out what is the maximum number of streams that we can have. So we set up this maximum number of streams, and because we will be declaring that number of streams and all that. So let's say we first initialize the host side arrays on which to work on. So let's say HA and HB are the host side arrays which are being malloced and pinned to the host side memory, so that we have support for asynchronous memory copy. And also we perform allocation for this GPU reference and host reference arrays here, right? And then we initialize all these data structures, host side arrays HA, HB, and then on the device side we actually create the different device arrays A, B and C, right, for the in the global memory, in the device global memory. Yes. So once this is performed, then for bookkeeping purposes we define two CUDA events, start and stop, and set them up here for recording, right? So we just create the CUDA events, and the moment we execute this function called CUDA event create, so the timing of whatever is going on next they will start recording from this point in the start and stop data structures, right? And then so here we just create the events, and later on when we will have CUDA event record, that is the point from which the start and stop events will actually start recording the timings, right. So, here we are just creating, declaring the events and creating their corresponding objects, and then we are just performing suitable declarations of the grid and block dimensions, using code similar to whatever we have discussed earlier, and we perform normal memory copy here just to show a normal execution. So, you copy the host side data to the device side data HA to HB, and you perform, and before this copy you actually start logging the timing using a CUDA event record in the timer start, in the event start, and here you record the timing for stop, and in between you make a normal kernel call for a for let us say this is a sum of arrays calculation for that kernel without using the asynchronous API, right. So, then